In this lesson, we're going to be identifying even and odd functions, graphing quadratic functions of the form f of x equals a times quantity x minus h all squared, graphing quadratic functions of the form f of x equals a times the quantity x minus h all squared plus k, and modeling real-life problems using f of x equals a times quantity x minus h all squared plus k. Even and odd functions. A function, y equals f of x, is even when f of negative x equals f of x for each x in the domain of f. The graph of an even function is symmetric about the y-axis. A function y equals f of x is odd when f of negative x equals negative f of x for each x in the domain of f. The graph of an odd function is symmetric about the origin. A graph is symmetric about the origin when it looks the same after reflections in the x-axis and then in the y-axis. For example 1, we're going to determine whether each function is even, odd, or neither. So for part A, I'm going to zoom in. I have f of x equals 2x. Well, what we're going to want to do is plug in negative x here instead of x. So I'm going to write f of negative x, and then we're going to see if it equals f of x or the opposite of f of x. If it equals f of x, then it's going to be an even function. If it equals negative quantity f of x, then it's going to be an odd function. And if it doesn't equal either of them, then it's going to be neither. So when I plug negative x in, all I'm going to do is change this x to a negative x. So this is going to be 2 times negative x. And that is equal to negative 2x. So f of negative x equals negative 2x. Well, if you notice, if I put a negative sign out here, negative f of x, that is also equal to a negative sign next to this 2x. So negative 2x. So f of negative x is the same thing as negative f of x. So this is going to be an odd function. So now we're done with part A. For part B, I'm going to move over. Now I'm going to do the same thing for g of x. I'm going to plug in negative x. So all that means is whenever I see an x in my function, I'm just going to change it to a negative x. So this equals quantity negative x all squared minus 2. Well, if I'm squaring a negative, the negative is going to cancel out. So this is just going to become positive x squared. So x squared minus 2 equals g of negative x. Well, if you notice, g of negative x is the exact same thing as g of x, because g of x also equals x squared minus 2. So since they're the exact same thing, this is going to be an even function. So now we're done with part B. For part C, I'm going to do the same thing. I'm going to plug in negative x where I see an x, and then I'm going to see if my function is either the same, the opposite, or none of them. So I have h of negative x equals 2 times the quantity negative x all squared, and then minus x, because this plus x is going to turn negative, and then minus 2. And then here I have negative x squared, which is going to just turn into x squared, times 2, minus x, minus 2. And now this is simplified. Well, I can clearly tell that this is not the same because my negative x here is not the same as this positive x. But it's not the opposite either. Remember, the opposite would mean I'd have to take the opposite of every term. So this would be negative 2x squared minus x and then plus 2. Well, that's not this either. So this is neither even nor odd. So this is just going to be neither. All right, so now we're done with example 1. Graphing f of x equals a times the quantity x minus h all squared. When h is greater than 0, the graph of f of x equals a times the quantity x minus h all squared is a horizontal translation h units right of the graph of f of x equals a x squared. When h is less than 0, the graph of f of x equals a times the quantity x minus h all squared is a horizontal translation, the absolute value of h units left of the graph of f of x equals ax squared. The vertex of the graph of f of x equals a times the quantity x minus h all squared is h comma 0, and the axis of symmetry is x equals h. Now this h right here behaves in the exact same way that the h behaved in absolute value equations in vertex form back in chapter 3. Because the h is on the inside of the function, in this case the function is whatever's being squared here, this is going to be a horizontal change, and if you remember, the things on the inside of the function are reversed, or I like to say a little wonky. So minus h is actually going to move it to the right, and then plus h, if we had a positive, if it was x plus some number, it would actually move that to the left. For example 2, we're going to graph g of x equals 1/2 times the quantity x minus 4 all squared, and then we're going to compare it to the graph of f of x equals x squared, the parent function. So whenever I'm graphing, I'm going to want to make my table. So I'm going to make a table of values here. And my middle value is actually going to be 4 here because, 1, I have a horizontal translation of my vertex, which is going to be 4 units from 0, and it's going right because it's this minus here. And if you remember, this h value right here represents the x component of the vertex. So this is going to be 4. I'll put that in the middle. And then since I don't have a constant term being added here yet, this is just going to be 0 for my output. And you can do that out here. If you plug 4 in, you get 4 minus 4 is 0, 0 squared is 0, 0 times 1/2 is 0. So we still get 0 here. Anyway, I'm going to count by 2s here, I believe, because this is what I'm counting on my graph. So I'm going to have 6, and then 8, 10. This will be 2, 0, -2. So I'm going to pick values and plug them in. So I'll do 6 right here. So 6 minus 4 is 2. 2 squared is 4. Half of 4 is 2. So this is going to be 2, and so is this. Because remember, this is my vertex, which means that this is where my axis of symmetry will be. So it'll be 2 and 2. Now I'll plug in 8. Well, 8 minus 4 is 4. 4 squared is 16. Half of 16 is 8. So that'll be 8. And so will this. And let's see if I can fit one more. I'll do 10. 10 minus 4 is 6. 6 squared is 36. Half of 36 is 18. That will fit. So I'm going to put 18. Now I'm just going to plot these points. So I'm going to plot them in blue because I'm going to be graphing the original parent function afterwards. So this will be 4, 0, and then 6, 2. I'll do 2, 2 as well, and then 8, 8, 0, 8, and then 10, 18. So it'll be at the very top. That'll be -2, 18 as well. I'm going to sketch my graph right now. Anyway, so there's my sketch. Now I'm going to make another row on my table just to graph the parent function. So this is going to be f of x. All right, and this is going to be pretty easy. So I'll start at 0 here because 0 squared is 0. And then 2 squared is 4. So this will be 4 and 4. And then 4 squared is 16. And then I would have 16 over there. And that's it. That's all I'll do for now because that's all that's going to fit. So I'll do this one in pink. So I'm going to plot the origin, 0, 0, which will be right here. And then I'm going to do 2, 4, so it'll be right here. And then I'm going to do 4, 16. Okay, now I could do 3, 9 right here. And then all these symmetrical points here, so it'll be right there. I could do 1, 1 as well. Something like this. And then over here, and right here. All right, now I'm going to draw my parabola through this. So now that I've sketched out my parabolas, now I'm going to describe the transformations from the parent function to g of x. So first of all, I see that this 1/2 is happening on the outside of my function. Okay, so this 1/2 that's happening on the outside is going to be a vertical change, and since it's a fraction in between 0 and 1, that's going to be a vertical shrink with a scale factor of 1/2. So I'm going to write that down. So vertical shrink with a scale factor of 1/2. Okay, there's no negative sign on the outside, so that means that there's not going to be a reflection. Okay, and now this -4, as you can see, this means that I'm translating this function 4 units to the right. And because it's -4, I'm going to the right. If this was +4, it would go to the left. So then I'm translating 4 units right. Now, you could say that you're translating the vertex 4 units right, but if you say that we're doing our stretches or shrinks first and then we're translating, that's fine too. Anyway, I've successfully graphed both of these functions and then compared them, and now we're done with this one. Graphing f of x equals a times the quantity x minus h all squared plus k. The vertex form of a quadratic function is f of x equals a times the quantity x minus h all squared plus k, where a does not equal 0. The graph of f of x equals a times the quantity x minus h squared plus k is a translation h units horizontally and k units vertically of the graph f of x equals ax squared. The vertex of the graph of f of x equals a times the quantity x minus h all squared plus k is h comma k, and the axis of symmetry is x equals h. Anyway, the only difference from the last example that we just did is we've now added this k. And remember, a plus k on the outside of a function, remember the function here is the x being squared, the outside of the function adding this k, all that's going to do is translate it vertically. So I'm either going to be moving it up if it's a positive number or shifting it down if it's a negative number. For example 3, we're going to graph g of x equals negative 2 times the quantity x plus 2 all squared and then plus 3. And then we're going to compare that to the parent function of f of x equals x squared. So the first thing we always want to do is identify our vertex. And our vertex here is going to be negative 2 comma 3, because to figure out the x value of the vertex, you just take whatever is inside of these parentheses and set it equal to 0. Well, x plus 2 equals 0. My solution would be negative 2. So my x value, my vertex, I'll write that down, is going to be negative 2. And then my y value is just whatever this constant is, because the vertex is either the lowest point or the highest point on your parabola, and that is going to be when this whole thing is equal to 0. And then when this whole thing is equal to 0, this entire part of the function drops out, and all I'm left with is this constant term on the outside. So it's going to be my output for the vertex, which is 3 here. So now I'm going to make my table of values. And I'm making it tall in anticipation of making my f of x equals x squared table as well. But first, I'm just going to start with x and g of x. Okay, and now I always want to have the middle of my table have my vertex in it. So I allowed 7 spaces here. So I'm going to put this right here. So negative 2 comma 3 will be right here. And I'll zoom out a bit. Scroll, I should say. Anyway, now I want to pick values that are near this, negative 2. That's my vertex. So I'm going to do negative 1 and 0. And I'll do 1 here. This will be negative 3, negative 4, and negative 5. Okay, they're all in there. And we'll see how many I can fit. Anyway, now I'm just going to plug some of these values in. So I'm going to start with negative 1, okay? Because negative 1, if I plug that in, I get negative 1 plus 2 is 1. 1 squared is 1, times negative 2 is negative 2, plus 3 is 1. Okay, and remember, this is my vertex, which means that my axis of symmetry tells me that my outputs the same distance away and x are going to be the same. So this is 1 away from negative 2, this is 1 away from negative 2, so they're going to have the same output. Anyway, now I'm going to do 0. So 0 plus 2 is 2, 2 squared is 4, 4 times negative 2 is negative 8, plus 3 is negative 5. And then I'll do 1. 1 plus 2 is 3. 3 squared is 9. 9 times negative 2 is negative 18. Plus 3 is negative 15. That's not going to fit, so I'm not going to bother with that. Anyway, I will graph g of x in blue. Let me zoom out a little bit. There we go. So first I'll plot my vertex, negative 2 comma 3. Now I'm going to do negative 1, 1. And then negative 3, 1. And then I will do 0, negative 5, and negative 4, negative 5. Now I'll sketch my parabola. Going to round it out so it doesn't look too pointy, because they're not pointy, it's smooth. Anyway, close enough. Now I'm going to graph f of x equals x squared, and I see that I took up the entire table that I made, so that was kind of a waste of time. So I'll just make another row and more columns. All right, so now this is f of x, and all I have to do is square my input. So 0 squared is 0. I get 1 and 1. This is going to be 4. 9, 16, and 25. Well, that's not going to be able to fit. neither will this. So I'll graph these points. So 0, 0 will go right here. Do this in pink. And then 1, 1 goes right there. And then I could do 4 for -2, and that will fit over here. So I'll do that right there. And that's all that's going to fit. So I'm going to sketch my parabola. Anyway, now I need to compare f of x and g of x. So starting from f of x, if you see what's happening here, I'm going to be reflecting this because I have a negative on the outside, and then I'm going to be stretching it by a factor of 2 because this 2 is on the outside. Remember, that's a vertical change, and since 2 is larger than 1, it's going to be a vertical stretch. I just want to write that down first. And it's always a good idea to start with your stretches and reflections, and it doesn't matter which one out of those two you do first. So I'm going to do a reflection in the x-axis, because that's acting as my mirror. And then, after that, I'm going to stretch it out. So vertical stretch with a scale factor of 2. And then all we have left is the translation. Okay, so at that point, I would just have this blue graph, but the vertex would be 0. So what I'm doing is I'm translating it 2 units to the left because of this plus 2. And then I'm translating it 3 units up because of the plus 3. So translate 2 units left and 3 units up. Anyway, I have now successfully graphed both of these functions and compared them, and now we're done with this one. So for example 4, we're going to take a look at the function that we just graphed in example 3, but now we want to graph f of x equals g of x plus 5. Okay, so if you remember at the very beginning, we dealt with even and odd functions. We plugged in negative x wherever we saw an x. Well, this is going to be very similar. What we're going to do is we're going to plug in this x plus 5 where we see an x here. So I'm going to rewrite f of x as f of x equals, and then I'm going to write g of x, which is -2 times, and then instead of writing x plus 2 here, I'll do this in a different color. I'll do it in green. I'm going to write x plus 5, and then that will be plus 2, because all I'm doing is I'm changing my x here. This is g of x. So g of x plus 5, wherever I see an x, I just put an x plus 5. And then this will be squared, and then plus 3. Okay, well, I can combine 5 and 2 to get 7. So this is going to give me -2 times x plus 7 quantity squared, all plus 3. All right, and now I want to graph this function. Well, the only difference in these two functions is that this vertex is going to be changed, because now my x value that would make this 0 is going to be -7. So the new vertex is going to be -7, comma 3, because this plus 3 on the outside is still the same. So now I'm going to make my table of values here. So I have x and f of x. So I have -7, 3. This will be -6, -5, -4, and this will be -8, -9, and -10. So if I plug these in here, -6 plus 7 is 1. 1 squared is 1 times -2, that's -2, and then plus 3, that's 1. So I get my 1s here. Remember, this is where my axis of symmetry is, so I can have a 1 here and here. And then same thing over here, -5 plus 7, that's going to be 2. 2 squared is 4. I'm going to get -8 when I multiply that. Plus 3, that's 5. And this one will not fit on our graph because we did that in our last example. Anyway, I'm going to plot these. So -7, comma 3. That's going to be right there. I'll do this in green. And then -6, comma 1, and -8, comma 1. And then -5, comma -5. I'm looking now and I forgot my -5s on the table. I apologize for that. Anyway, I'm going to go down and do -5, -5. And then -9, -5. Now I'm going to sketch this. Anyway, we've successfully graphed this. It doesn't tell us to describe it, but all we've done is just translated this g of x 5 units to the left. That's what this plus 5 did right here. That is a horizontal translation, 5 units left. Anyway, now we're done with example 4. For example 5, water fountains are usually designed to give a specific visual effect. For example, the water fountain shown consists of streams of water that are shaped like parabolas. Notice how the streams are designed to land on the underwater spotlights. Write and graph a quadratic function that models the path of the stream of water with a maximum height of 5 feet, represented by a vertex of 3, 5, landing on a spotlight 6 feet from the water jet, represented by 6, 0. All right, so there's a lot going on here, and the first thing I'm going to do is plot my points, but this graph that I have does not have a scale, so I'm going to scale it. So I'm going to zoom in. So my y-axis is going to be my vertical feet, my height, and then this is going to be my length, horizontal feet. So this is in feet, and this is feet as well, but it's not letting me move it there, so that's in feet. Anyway, now I'm going to plot my points. So my vertex of 3, 5, so that's going to be right here. And then I have the water hitting the light at 6, 0. It's right there. Now, given all this information, I need to write and graph a quadratic function. Now, 2 points is actually technically enough if one of them is the vertex, because I can use the axis of symmetry to plot this point over here. So this is 3 units from the vertex, so I'm just going to do 3 units the other direction from the vertex, which is going to give me 0, 0. Okay, but writing a function is going to be a little bit trickier. I'm going to use vertex form. This would work if we had used standard form as well, but vertex form is going to be a little easier. For vertex form, I have y equals a times x minus h squared and then plus k. Well, I know my vertex. My vertex is 3, 5. So I'm going to plug in 3 for h and then 5 for k. So I have y equals a times x minus 3 all squared and then plus 5. All right, well, I also have a point on this parabola. So what I can do is I can plug this in for my x and y and then simplify to solve for a. So I'm going to plug in 6 for x and 0 for y. So I get 0 equals a times 6 minus 3 squared plus 5. All right, and now I'm going to simplify this. So I get 3 squared plus 5, and then the a is being multiplied by the 3 squared. So this becomes 9a plus 5, and I'm going to bring down my zeros. So now I'm going to subtract 5. And I get negative 5 equals 9a. I can divide 9. Negative 5 ninths equals a. So all I need to do is plug this back in up here, and then I get my function. So that's going to be y equals negative 5 ninths times quantity x minus 3 all squared, and then plus 5. So here is my function that I wrote. So what I did to solve this is I used the general equation for vertex form, which is y equals a times the quantity x minus h all squared plus k, and I plugged in my vertex. Remember, vertex is h comma k, so I plugged in 3 for h and then 5 for k, and then I plugged in 6 and 0 for x and y respectively to solve for a. When I solved for a, I got negative 5 ninths for my a value and put it all together to get this equation. Now, like I said earlier, technically 3 points is enough to have a unique parabola, but I'm going to add 2 more points on either side of the vertex just to make it a little bit better of a hand-drawn graph. So I'm going to plug in 1 and 2. So I'll start with 2. So if I have a table here. So I know my vertex is 3, 5. If I have 4 and 2 there, if I plug in 2, I get 2 minus 3 is negative 1. If I square that, I get positive 1. And then times negative 5 ninths is negative 5 ninths. And then plus 5, this is going to be 4 and 4 ninths. Next, I'm going to plug in 1. 5 would be the same thing. if I plug in 1, I get negative 2, and then when I square that, I get 4. So 4 times negative 5/9. Well, that's going to be negative 20 over 9, which is the same thing as negative 2 and 2/9. So when I add negative 2 and 2/9 to 5, that's going to give me 2 and 7/9. So I get 2, 7/9, 2 and 7/9. So I'm just going to do my best approximation of plotting these ordered pairs. So 2, 4 and 4/9, that's going to be about halfway in between here. So something like that. And then for my other values, 2 and 7/9 for 1 and 5, that is going to be close to 3, but a little bit below. So here would be 3, so I'm going to go somewhere like that. And there. All right, and now I'm going to draw my parabola. Now, I'm not including arrows here just because of the context of the problem. I'm starting at 0 because that's where the water is shooting out, and then it is landing back in the water at 6 feet. Anyway, I'm going to look up to make sure that I've answered all my questions. So I've successfully written my quadratic function, and I've successfully graphed my quadratic function that models the path of the stream of the water, and now we're done.